shit, I was muted this entire time. Yo, look at this chicken teriyaki. Yo, look at this. Look at this chicken teriyaki. search tree is a type of binary tree in which the data is organized and sorted over. Oh my god. Alright. All nodes in the left subtree of any node contain. All nodes on the left. Contain smaller values. All nodes on the right contain larger values. Both the left and right. Both left and right are binary search trees in their own respect. As well, the value on the left subtree is less than the parent node, which is less than left, less than parent, less than right. What the fuck? Ah, thank you, Jazz. I'm trying. So all of these are log of n, searching, inserting, deleting. But the worst is O of n if we gotta traverse the entire tree. So we start from the root, compare the value you want to search with the root. If the swip. Oh yeah, this is what I was exactly. Okay, cool. Let's see. I mean, you input an array, right? Yeah. So we gotta make a struct called node. Alright, you have a good day, Jazz. Thank you. So we're pointing. There's a pointer to the left node, and then we got a pointer to the right node. Right. Okay, so those are the attributes of one node. I'm trying to read this, if this makes sense. Okay. So we return a pointer to a node. I'm trying to like speak this out so that way I know what I'm talking about while I type it, so that I'm not just blindly typing. But this is my first time seeing it, so I'ma just write it as is, and then try to memorize and see how it works line by line. So, in order, you gotta call the node. Well, you gotta create a new node. New node equals new node, and then we put data. The data would be whatever's in the left, and no, data new node right. I mean left is equal to new node right. Okay, they're both null pointers. Then we're returning the new node itself. Alright, so that's for the create node function. Okay, so we gotta insert. Oh my god, we need a function to insert a node into the binary tree. Okay, this is to traverse in order. Okay, we're searching for a given key, minimum value, delete node, and then we got cool. Oh, that seems pretty straightforward. Oh my god. Nah, I can't be doing this on here. Shit. Oh, fucking hilarious. Oh no, not my phone. All right. Okay. So we have why am I getting errors? using? What you mean? Hmm. Close that up. Why am I variable using is not a type name? What do you mean? Oh, I'm dumb. I'm writing this in C. How do I rename this? Whoops. How low am I? Alright, right? That makes sense. Okay. Equals. So then we're returning a node, we're inserting. No, we need the no pointer. We need the root, and then we need int data. Okay, so I'm gonna just speak everything I see out. So if the root is equal to a null pointer, it means the tree is empty. Create a new node. Okay, so then we use return create node, and then we put the data that was passed through. Right. If the data is less than the root's data, we want the root left node to equal, and then we're gonna insert node, and then we're gonna put data. Whoops. Okay, so if the data is less than, no, oh, if it's greater than, no, if it's less than. Yo, these two symbols will always confuse me until the day I die. We're inserting a node, so data is less than the root. It's equal to its own node. Okay, so then if we're inserting a node, okay, so this becomes a root node too, right? Right. the left. We pass the data. Right. That makes somewhat sense. Else if the data is greater than the root's data, we make the root of the right, and then we insert a node root right, and then we pass the data as well. We're returning the root. So, alright, I guess that makes sense. If the root equals a null pointer, that means the node, the tree is empty. Tree is empty. Right, okay, cool. If the data is like less than the root's data, the root's left, we will insert a node. Root left. Left data. Oh yeah. Because each node is its own tree. Both left and right are their own binary search trees as well, so it's gonna recur. Okay, it's gonna recursively go. Then we return to root. All right, so traversal. So we're not returning anything. Passing the new node's root. If the root does not equal null pointer, oh my god. Oh, I cannot type. So we're doing an in order traversal. Going through the left. Then we see out this data. The roots, root, data. Put a space and then we print out the right. Right, okay, cool. So now given key search BST. Alright, so we're gonna search the node, we're passing the root node, and then we're passing the key we want to find. Right, okay. If the root null pointer or the root, okay, so this is if the first element is already the key. Immediately stop searching, and we already found it. This would be O1 constant since it's found right away. Cool. And then we return root. Okay, so if the root's data is less than the key, we're gonna, if the root's data is less than the key, we're gonna search data is okay. So yeah, so if the roots, oh what? Okay, root data less than the key. Oh, okay, okay. So say this was 6 and this was 7, we'd go on the right. Okay, cool. Root right. Key. Oh my god, my brain hurts. Okay, but it hurts so good. I actually get it. Where? Nah, bro, I'm this is ridiculous. Ah. Alright. Oh, then if, yeah, so if the key's smaller, okay, so then the only other option would be to check the left side. Let me pass the key as well. And then what are we, hurts? Oh no, these are what are we returning? Okay, cool, cool. My god. To find the in order successor? No. No node. The current node is equal to a node. Loop down to find the left. Oh, okay. So this is to find the minimum, the smallest value in the entire tree. Okay, node, min value node. Node, pass a pointer, node. Okay, so then we make node. We're pointing to a node and we're putting it in current. We're calling it node. Okay, cool. Where am I looking? Okay, so while the current node while they don't equal a null pointer, we can make current equal to current left. I mean, we only have to search the left because that's where all the minimum values are. Oh man, why's my phone bugging up? Sir, please help me. What do you need help with? I need help myself too. I'm here trying to learn, as I hope you guys are as well. How can I use NetBeans? NetBeans. For Java, I can't really help you. I don't code in Java. Sorry, man. And then we return current. You might want to just YouTube solutions. Honestly, the mindset to have is that if you're having a problem, you gotta be able to search up for the solution. This might take you a while, but it's trial and error. You're not gonna get everything right the first time. If you want a code, you could definitely use VS Code. VS Code is lovely. This is where I'm coding my algorithms in. You could see. Alright, doing a node point. We're returning a node. We're deleting the node. And what are we passing? The node's root. Yes, of course you could use VS Code. So if the root equals equal to a null pointer. Alright, so we always start with the base case first. We always start with the base case first, and then we type it in. So if it's a null pointer, we just return, which is nothing. Okay, that makes sense. So then, if the data is less than the root's data, if the data to be deleted, if the data to be deleted is smaller than the root's data, then it lies in the left subtree. Okay, that makes sense. That makes sense, right? So we go to the root left, and then we delete the node. I know I'm copying this code word line by line, but being able to write it out and actually like try to understand it line by line as I type it out actually does help. Imagine it, now if I just copy and pasted all of this and try to figure this out myself from, yeah, I'd rather talk it out and then type it once I get an understanding of what it's doing. Alright, so now if it's not on the left, it's going to be on the right. If the data is greater than the root's data, it's going to be on the right. Oh. Alright, so yeah, if the data is on the right, no, if the one that's going to be deleted is on greater than the roots, it's going to be on the right. So then the root's right. We're going to delete the node. We're just going to traverse this. I gotta remember that every... Yes. A vape keeps me sane. I also got my chicken teriyaki on deck. It's a good night. If data is same as roots data, then this is the node to be deleted. Cigarettes. I only smoke cigarettes when I'm drunk, and even then. Actually, yeah, when I'm drunk is the only time I'll smoke a cigarette. And I haven't gotten drunk in a minute. So if the data is the same as the roots data, this is the node to be deleted. Okay, so this is where we're doing the deletion. So okay. So then if the roots left is equal to a null pointer. Okay, node with only one child or no child. Oh, okay. Yo, just chat GPT the answers at this point. Can't really help you. Why am I getting an error here? What is this? Oh. Alright, so then at this point, so if only has one child, so the roots left is a null pointer. Is equal to a null pointer. What are we doing? We're making a temporary node. Make it temporary node. Delete the root and return the okay. If the data is same as what did it mean? Okay. And we return the temp node. The roots rate is equal to a null pointer. Make a temporary node, and then we put the root left. Okay, that's it for Dados. Node with 2 children. Get the in-order successor smallest in the right subtree. So we create a new node named tab, and then we traverse the right side of the node, of the root node, right? Copy the in-order success. Okay, so we're copying the roots data into this temporary node. Temporary data. These are all structures. That's why we're using the arrows. The root's right. We're deleting the node, and we're putting the root to right, and then we're passing the temp data. Right. All right, cool. All right, so I somewhat understand this more now than I did like 20 minutes ago. See, the problem with me is that C++, it's so verbose. I mean, Java's more verbose, but like, I want to learn C++. Why? It's harder, and I like a challenge. I could be doing this in Python, and I probably am shooting myself in the foot not doing this in Python, but hey, fuck it, we ball. Alright, so this is the output now. Alright, this is the main function. This is where we're going to put in all our data. So what do? We create a node with the null. I'm gonna call it root. We're gonna put a null pointer, and then it's gonna be empty. It's gonna have a null pointer. So to create a binary search, we gotta make all these roots. We gotta insert all these roots. Cool. I'm gonna just copy and paste these. I'm not typing all that out. Right. 50, 30, 20, 40, 70, 60, no specific order. Print the in order traversal of a BST. Okay, so cool. We're printing root. So we're now printing out the traversal order. Wow. Traversal of BST in orders. And then we do the in order. We do the in order traversal root. Alright, so this is for the traversal. To delete a node. Alright. Say we want to delete node 20. Pass the root, and then we pass 20 to be deleted, right? Right. And then after deletion, alright, so this is going to print out the order once we delete 20. And then rerun it in order. Why is my function? Why am I? So to insert node equals insert a node and bring the root as 25. Is this thing dying already? No way. Oh man, I just bought this like a couple days ago. Okay, so then after the insertion of 25, we're gonna traverse the tree again. Search a key, okay, so then okay, we're looking for 25. Check if key is found or not. Alright, I'll just okay, no. So then if found does not equal pointer, no pointer. Else. Sad face. Will that give me an error? Nah. And then to finish it all off, we return 0. Cool. Alrighty. More in control. Whatever that means. Okay. Alright, cool. So 20, 30, 40, 50, 60, 70, 80. Alrighty, why is this not printing? After deleting 20, in order to traversal root, Alright, I'm getting an error. Where did I mess up? Okay, so why is this not working? Alright, after the insertion of in order to traverse the root, right? The comments on here. Hades, yo, in order blah 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 blah. Count 20. What does this mean? Control to send from on. Oh, whoops! I didn't return the root. Whoops. Oh wait. Oh, duh, silly me. Parentheses, gotta love them. Alright, cool, awesome, fix it. See? Shit like that pisses me off about coding, man. But you have to be very precise. The computer does not know what you want, only you know what you want. Traversal of BST, okay, 20, 30, 40, 50, 60, 70, 80. After we delete 20, it's 30, 40, 50, 60, 70, 80. After we insert 25, 25, 30, 40, 50, 60, 80. And it found node 25 after inserting it. Cool. Alright, let's push this there. My church. Alright. Alright, let's read. Let's read, shall we? After writing all that down, binary tree nodes have a left and right field, left and right pointer fields, right. Left and right pointers. And an optional parent pointer. Okay, cool, we don't need a parent. Okay, so it has the data, the left and the right at least. It doesn't have to have the parent. The binary search tree labeling uniquely identifies where each key is located. Start at the root. Okay. So we're passing the root and then the data. Well, what we're looking for. Unless it, okay, X is the key here. So if the root, yeah, so this is the root. They just called it tree here. If it equals null, return null. Okay. Well, I mean, yeah, we're basically doing the same thing here. Root equals null pointer, return root, which is null pointer. Alright. If the data is equal to, okay, or if the data is equal to key, we return the root. Okay, so that way we don't write two separate lines. Cool. If root data is less than the key, we're oh, okay, we're doing it opposite here. Why? If X is less than, if data is less than the key. Oh yeah, I forgot we're doing it backwards. It's kind of confusing. Can't I just root? If the key is less than the data, no. If the key is less than the root data, you can search the left and the right. That's less confusing, right? Yeah, okay, cool. That makes more sense. Alright, so yeah. If X is less than the tree's item, then the current node's item, we search the left, else we search the right. Alright. Minimum and maximum elements. Implementing the find minimum of by definition, the smallest key must reside in the left subtree of the root, since all keys in the left subtree have values less than that of the root. Therefore, as shown in figure 3.3, the minimum element must be the leftmost ascendant of the root. The minimum element must be in the leftmost ascendant of the tree. Similarly, the maximum element must be in the rightmost. Okay, so maybe this is the equivalent. Okay, so where I mess up is writing code in different ways. You see how we have this here and then we have this here. Alternating between different languages and ensuring that it's the same implementation is something that I always get confused about, because this is written in C, this is all C, this is C++, so it's a little bit, it could be the same, but it's different. Okay, find the minimum tree man pointer min if the, okay, no, equals T. Okay, that's what we got here. Pretty much current, I guess. Instead of min, called it current. While min left does not equal null. Current, okay, return, okay, cool. Traverse the tree, visiting all nodes in the root of binary trees through blah 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 blah. Cool. Chapter 5. A prime application of tree traversals listing all the labels. Is listing the labels of the tree nodes. Binary search trees make it easy to report the labels in sorted order. By definition, all keys smaller than the root must lie in the left subtree of the root. All keys bigger than the root. Right, okay, yes, we know that. Blah blah blah. An in-order traversal of the tree. Where is our in-order? Okay, if it does not equal null, traverse the tree left. We print out the item and then we traverse the rights of the root, and then we do that. Wait, no. Oh, okay. So here, look, we got 20, not pointer, 20. Inward traversal, 20. To the right. What else? Each item is processed once during the course of the traversal, which runs in O of n time, where n denotes the number of nodes in the tree. Cool. Okay, insertion in the tree. There is only one place to insert an item X into the binary tree where we know we can find it again. We must replace the null pointer found in T after an unsuccessful query for the key K. This implementation uses recursion to combine the search and node insertion stages of key insertion. The 3 arguments to insert. I mean, a pointer. Alrighty. Oh, damn, we're using them a lot. Yeah, I hate C. C++ is tolerable though. Allocating the node O of H. Deleting tree nodes with 1, 2, 0, 1 into each other. Oh, that shit's so good. So when we delete, yeah, see, if we delete 6, we gotta be able to put 5 up here with 4. Oh no, what are we? Oh, we're deleting 3. Okay, first here. And then we delete node with 1 child. We're deleting 6. Put 5 with the 4. Oh my god. Because removing a node means appropriately linking its 2 descendant subtrees back to the tree somehow. There are 3 cases, blah blah blah. Okay. 0 children, 1 child, and 2 childs. Okay, so if it has 0, we could just delete it. When implemented using binary search trees, all 3 dictionary operations take over each time where h is the height of the tree. The smallest height we can hope for occurs when the tree is perfectly balanced, where h equals log of n. This is good, but the tree must be perfectly balanced. Alright, so log of n, log of 8 would be what, 3? La 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 la. Alright, cool. Alright, I think that's it for today. So we implemented this binary search tree. Let me go over it again, speak it out loud. So first we create a struct node containing int data, and then it also has a pointer to a left and a right node. We create a node and insert the data. We create a new node inside this function, new node. And then the new node's data is equal data. New node's left, new node's right is equal no pointer. There's nothing there yet. We return the new node. Okay. New node equals new node. Okay. Insert node. You create the node and okay, cool. If the data is less than the roots data, if the data is less than the roots left would be inserted. We're inserting a node on the roots left with the data. If it's greater than the roots data, the roots right, we insert a node, root right data. Then to traverse, well, it's not a null pointer, traverse the left, and then print it out, and then the right. La-di-da-di-da, la-di-da-di-da. Alright. I get the core concepts. I mean, we run it again, you can see it works. Alright. Well, that's all the studying I'm gonna do for tonight. I am about to get off. But thank you to whoever joined me tonight. It's just a little calm stream. I'm just on here trying to look at this stuff and learn more of it. But yeah, alright, that's it for me today. Thank you guys and have a good night.